equations. All right, so the equation that's written at the top of the page here is the equation that we looked at on page 5, the silver nitrate reacting with potassium chloride, producing the silver chloride precipitate and aqueous potassium nitrate. The difference is that everything is separated out into ions, so kind of like if you had drawn it in the beakers, this is what you would see. All the ions are separated from each other, with the exception being the precipitate, because when something precipitates, it does not form ions. So look at the before and after the reaction. So that's separated by the arrow. Before the reaction and after the reaction, a couple of things are the same. What do you notice is the same? Specifically, are there things that are appearing in both the reactants and the products in exactly the same form? What do you see?
The nitrate and the potassium stays the same.
Good. The nitrate and the potassium are both aqueous ions before and after the reaction. So in the notes you can write down the K plus and NO3 minus ions are present in the solution before and after the reaction. So they appear unchanged in both the reactant and product sides of the reaction. We call them spectator ions, right? Like spectators at a sporting event. So think about like the parents at a Little League game. The parents at a Little League game have no effect on the outcome of the game, right? It's the little kids playing. That, you know, they score the runs, they hit, they catch, they run the bases, all that stuff. But the parents are just cheering and watching. They're not actually doing anything in the game. So spectator ions are the same thing. The potassium and the nitrate are unchanged before and after the reaction. The actual reaction that's happening here is silver ions and chloride ions are combining to form solid silver chloride. So spectator ions are ions that appear on both sides of a balanced chemical equation. They do not participate in the net reaction. So in the net reaction is saying they don't participate in what's actually happening. They're not part of the change. They only look on from the sidelines. So think of the net reaction as being what gets written down in the scorebook, right? At a Little League game, the batting order, who bats in the inning, the positions of all the players, all of that gets written down in the scorebook. But they don't write down who was there watching the game, right? That would be crazy to write all that down. So at a sporting event, only the stuff that goes in the scorebook is what's actually happening in the game. Same thing here. The net reaction, the net ionic equation is what's actually happening, what's changing here. Little chemical information about the reaction is lost if the spectator ions are omitted, so the equation can be simplified. So what I'm going to do is I'm going to cross off the things that are aqueous before and after the reaction. So that would be the nitrate and the potassium. And all I'm left with is the solid product and the aqueous ions, that formed it. So the chloride and the silver. So the net ionic equation for this reaction would be Ag plus aqueous plus Cl minus aqueous produces AgCl. S. That would be the net ionic equation for this reaction. So it's only showing what actually changed in the reaction. Because the potassium and the nitrate didn't change, they are not included. They're aqueous before and after. Nothing changed about them. And you saw that when we modeled on page 5 in the drawing. So you had aqueous potassium and aqueous nitrate ions in the beakers before. After the beakers, you drew them aqueous, just in the same place. So the net ionic equation is a balanced equation that results from leaving out the spectator ions. So we crossed them off, and then the thing that we wrote was only the solid product and the aqueous ions that formed it. So only the solid product and ions that changed in the reaction are included. We would leave out things that are not changed, and we would leave out non-electrolytes. So non-electrolytes would be things that either, well, let's make the list. Non-electrolytes could be insoluble compounds. So that would be the precipitate because it's insoluble. The other thing that you may run into, especially in the homework problems that we look at, would be if you had a soluble, so able to dissolve, molecular compound. So remember when I did the light bulb thing last week and the sugar did not light the light bulb? The sugar was a non-electrolyte because even though it dissolved, it did not produce ions in the solution, so therefore it didn't conduct electricity. So even if it's soluble, if it doesn't produce ions, if it's molecular, or another word for it is if it's covalent, it's a non-electrolyte because it can't conduct electricity if it doesn't produce ions. And then gases. So sometimes in the reaction you would have these other things that are part of the reaction but they're not ionic, so you would include them in the net ionic equation anyway. And then the other thing that I wanted to point out to you guys is that the potassium and the nitrate, they aren't totally useless here. All right, so we crossed them off because they're not changing. But their purpose was to accompany the silver and the chloride ions in the solution. They were used to accompany the silver and chloride ions in the solution. So kind of like the parents at the Little League game, right? The kids need the parents to bring them to the game, correct? That's why the parents are at the game in the first place. Also, they love their children. But I can't go into my stockroom and just get only potassium ions. I don't have a jar of just potassium ions. It's always bonded to something else, right, in a compound. Same thing with nitrate or silver or chloride. So you always have a compound that contains the ions that you need. So the K plus and NO3 are needed to accompany the Ag plus and Cl minus in the solution. Now, granted, any other set of ions could have done that. All right, so you can say any cation and anion would do. So for example, if let's say, I don't know, AgClO4 and KCl were combined. So instead of having the nitrate, now I have a different ion here. My net ionic equation is going to be the same. And I'll show you about that. So I'm going to erase and scroll down and write down what's going on here. So in the reaction that I just suggested, I would have Ag plus, which is aqueous, plus ClO4 minus, which is aqueous. So I substituted that for the nitrate, plus K plus aqueous plus Cl minus aqueous. So that's going to produce AgCl plus ClO4 minus, running out of room, plus K plus. So again, if I look at my reaction and cross off the things that are aqueous before and after, I'd be crossing off the chlorate, the potassium before and after, and I'm left with the same net ionic equation. Ag plus Cl minus produces AgCl. So those spectator ions really don't have any effect on the net ionic equation. They're just there to accompany the ions that we care about to the reaction as the other half of the reactants. Important thing, there must always be a mass balance as well as a charge balance on both sides of the equation. So you guys know what a mass balance is. We don't really call it that, but that just means that the law of conservation of mass is obeyed. So you have the same number of each type of atoms. If you've done it correctly, the charge balance will come right along with it. You won't have to do anything additional. But what that means is, if you look at AgCl, that's a neutral ionic compound, so the charge on the right side is 0. So the charge on the left side should also equal 0. I have a positive silver ion and a negative chloride ion. Cancel each other out, equal 0. So as long as you've written your charges correctly, mass balance and charge balance should go hand in hand. So that's the end of the material that we're going to cover today. So on page 8, just a couple of practice problems. I'll do one with you, and then I'll let you guys work on this on your own. All right, so top of page 8. It says, write a balanced net ionic equation for the reaction of aqueous solutions of barium chloride and sodium sulfate to give barium sulfate and sodium chloride. So for this one, it's nice, I already gave you the formulas for everything. So the first thing is to write the overall equation and balance it and write the solubility of each compound. So we're told that the reactants are aqueous. So I'm just going to go ahead and write down barium chloride, which is aqueous, plus sodium sulfate. Of course, you don't want to make a foolish error at this point and copy it down wrong. That would be unfortunate. Produces barium sulfate. I don't know about that solubility yet, so I'm going to leave a space to go back and write it, plus sodium chloride. So using my solubility rules, which obviously right now you guys are flipping back and looking at them, but by next week you should have them memorized so that you can just do it from memory. The sodium, that's an easy one. It's in group 1, so I'm just going to get that one out of the way right away and write down that it's aqueous. That leaves me to have to think about the barium sulfate. Do I have a rule for barium? If you look at your list, no rule for barium, so that means you have to look at the sulfate. Do you have a rule for sulfate? Which list is it on? It's on the soluble list, but the exception is if it's paired with something in group 2, which barium is. So barium is an exception that would make sulfate insoluble. So the barium sulfate is going to be my precipitate. So now that I've got the formulas written down and I know the solubilities of the products, now I'm going to write that big long thing out with all the ions kind of separated out. That way I can cross them out. But before we do that, I have to make sure it's balanced. Is it balanced? No. What do I have to do? I've got 2 chlorines here and 2 sodiums there, so I need a coefficient of 2 in front of the NaCl. If you forgot to balance it, then you would not have a mass balance and charge balance in the net ionic. All right, so you're going to want to use like every inch of the paper here. So start like way over at the edge of the paper, use more than the line that you're given. And I'm probably going to run out of room. So now we're going to separate everything out. So barium chloride is made of Ba2 plus ions that are aqueous. So you always have to write the states of matter here. Plus, how many chlorines go with it? 2. So I'm going to write that like this, 2Cl minus, because it's 2 chloride ions. All right, so you see how I took the subscript and made it a coefficient here? Because now I'm kind of writing it as its own reactant. Plus, same thing again, I've got 2 sodiums in sodium sulfate. Then I have this sulfate, which is SO4 2 minus. So you guys see how this is kind of detail oriented. You really got to pay attention to what you're doing. That's aqueous. That's going to produce me, I'm not going to separate the solid, right? Because as a solid, it's not going to dissociate. So I'm just going to write BaSO4 S plus, now I've got to deal with that coefficient. That coefficient means I have 2 sodium ions that are aqueous and 2 chloride ions that are aqueous. Once I have that step done, step 3, identify and eliminate the spectator ions. Write the net ionic equation. So for step 2, I'm going to cross off things that are aqueous on both sides. So what things am I crossing off here? What do we have that is aqueous before and after?
Sodium.
The sodium. So I've got 2 Na plus on the left side, 2 Na plus on the right side. They're aqueous on both sides, so I can cross them off. And then the chloride as well. 2Cl minus aqueous in the products, 2Cl minus aqueous in the reactants. So I'm crossing those off. And then to write the net ionic equation, I should have just the solid and the ions that form the solid that are not crossed off. So that would be Ba2 plus aqueous plus SO4 2 minus aqueous produces BaSO4 solid. So, a couple of things. This middle step, you only have to do if you're specifically asked to do it. I say that with caution. It's wise to do it. All right? Because some of the questions that you'll be asked on the homework, possibly on the quiz, is how many of each spectator ion are present. And that's a lot easier to see when you write it out this way. There's 2 sodiums and 2 chlorines. It's a lot easier to see with that coefficient. When you just write it with the formula, it's a lot easier to forget to do. I tell you this because we see it happen every year with multiple people. So as you're learning, it would be best to do this until you start to get the feel for it. So I would say on page 8, you should write out that middle step. So do all 3 steps on page 8, and then as you get more comfortable, if you feel like you're good, you can not do that middle step unless it's specifically asked for you to write out the whole big thing. All right, any questions on this? I know it's kind of a lot of information that we did today. It was all kind of related and building on each other, but if you have questions about any of the steps, now would be a good time to ask. It's not too inherently complicated of a topic. It just requires a lot of practice. It's detail-oriented, and you have to memorize the solubility rules. I have a Quizlet for you that I'm going to share right now once you guys start working that has, like, for example, say group 1 cations, and then you'd flip it over and it says always soluble. So you can use that to practice, but you should be able to have these memorized really quick. That way you know. So I'm going to let you guys work on the bottom of page 8. As you finish, I'll check it, and then you can start working on the homework, which I'll tell you once you're done.